Hi everyone, welcome to our physics class. In the previous class, we have studied about meaning of electromagnetic waves and properties of electromagnetic waves. What is the meaning of electromagnetic waves? Electromagnetic waves consisting of the time varying electric and magnetic fields, time varying electric and magnetic fields which are mutually perpendicular to each other and perpendicular to the direction of wave propagation. So what are the properties of electromagnetic waves? Electromagnetic waves are transverse in nature. The speed of electromagnetic wave is same as that of the speed of light. Accelerated charge particle radiates energy in the form of electromagnetic waves. Accelerated charge particle, actually that is the source of electromagnetic waves. So in electromagnetic waves, electric field and magnetic field, which are mutually perpendicular to each other and perpendicular to the direction of wave propagation. So the oscillations of electric field and magnetic field are in phase. They transport energy and momentum. So when electromagnetic waves strike the surface, when electromagnetic waves strike the surface, the pressure is exerted on the surface. They show the properties of reflection, diffraction, interference, diffraction, polarization. And the electric field is responsible for optical effects of electromagnetic waves. So those are some very important properties of electromagnetic waves. So name the scientists who first predicted the existence of electromagnetic waves. Hertz, right? Hertz is the scientist who first predicted the existence of electromagnetic waves. So what are the contributions of Hertz to electromagnetic wave theory? Hertz confirms the existence of electromagnetic waves. He produced stationary electromagnetic waves using V is equal to F lambda. He found that the speed of electromagnetic waves is same as that of the speed of light. So, who proposed electromagnetic wave theory? Maxwell, right? Maxwell proposed electromagnetic wave theory. And Maxwell explanation of electromagnetic wave theory. So that is very important on the basis of Faraday's laws of electromagnetic induction and modified Ampere's law. Maxwell theoretically predicted the existence of electromagnetic waves. According to Faraday's law of electromagnetic induction, the time varying magnetic field generates electric field. According to Maxwell modified Ampere's law, the time varying electric field generates the magnetic field. It means the electricity and magnetism are symmetrical. The consequence of this symmetry is the existence of electromagnetic waves. According to Maxwell, an accelerated charged particle radiates energy in the form of electromagnetic waves. Suppose if a charged particle oscillates harmonically with frequency mu, produces electromagnetic waves of same frequency. So what is the expression for the speed of electromagnetic waves? C is equal to 1 divided by square root of mu naught epsilon naught. That is in vacuum. In material medium, V is equal to 1 divided by square root of mu epsilon. So these are the topics we have studied in the previous class. Okay. So this is electromagnetic waves part 3. Okay, well, let's start today's class. So in this class, first we are going to discuss about electromagnetic spectrum. What is electromagnetic spectrum? Name the main parts of electromagnetic spectrum and giving their wavelength range. Okay, so electromagnetic spectrum means arrangement of electromagnetic radiation. Arrangement of electromagnetic radiation in the increasing order of their wavelength. That is actually called the electromagnetic spectrum. What is the meaning of electromagnetic spectrum? arrangement of electromagnetic radiations in the increasing order of their wavelength. Okay, so what are electromagnetic radiations? Gamma rays, X-rays, UV rays, visible rays, infrared rays, microwaves, and radio waves. Those are the radiations of electromagnetic waves. Okay, let us consider the chart. The first column containing the radiations, second one wavelength range, third one discovered by. So the first radiation, that is gamma rays, and then X-rays. After that, UV rays, ultraviolet rays. Okay, and then visible rays. After that, infrared rays. The last one, microwaves and radio waves. Microwaves and radio waves. So, what is the wavelength range of gamma rays? That is very important. So, the wavelength range of gamma rays, that is from 0.01 angstrom to 0.01 angstrom to 0.1 angstrom. Okay, so this is the wavelength range of gamma rays. The wavelength range of X-rays, that is 0.1 angstrom, 0.1 angstrom to 0.1 angstrom to 100 angstrom. So this is the wavelength range of X-rays. Okay, so the wavelength range of UV rays, that is 100 angstrom, 100 angstrom to 100 angstrom to 4,000 angstrom. So this is the wavelength range of UV rays. So the wavelength range of visible rays, that is 4,000 angstrom to 8,000 angstrom. So this is the wavelength range of visible rays. Okay. So and infrared rays, the wavelength range of infrared rays, that is 8,000 angstrom to 4,000 micrometer. And the last one, the wavelength range of microwaves and the radio waves, that is 4,000 micrometer to 10 power 5 meters. So this is the wavelength range of microwaves and radio waves. So who discovered gamma rays? This is very important. Willard. Okay. So gamma rays was discovered by Willard. So who discovered X-rays? That is Rontgen. Okay. Rontgen discovered X-rays. Who discovered UV rays? Who discovered UV rays? Ritter. Okay. UV rays was discovered by Ritter. Who discovered visible rays? Newton. Okay. Visible rays was discovered by Newton. Who discovered infrared rays? Herschel. Herschel. Infrared rays was discovered by Herschel. Microwaves and radio waves, Hertz. Who discovered microwaves and radio waves? Hertz. So gamma rays was discovered by Willard. X-rays was discovered by Rontgen. UV rays was discovered by Ritter. Visible rays was discovered by Newton. Infrared rays was discovered by Herschel. Microwaves and radio waves was discovered by Hertz. Okay, so this is very important. The wavelength range and discovered by. What is electromagnetic spectrum? Arrangement of electromagnetic radiations in the increasing order of their wave. Okay, now let us discuss about the uses of electromagnetic radiations. First one, the uses of gamma rays. So gamma rays are used for the treatment of cancer. The first one, gamma rays are used for the treatment treatment of cancer. Okay, and then gamma rays are used in industries to kill the harmful bacteria. Okay, gamma rays are used in industries industries to kill harmful bacteria harmful bacteria, and it is used to detect heart and brain abnormalities. Okay, so it is used to detect heart heart and brain abnormalities abnormalities. And gamma rays used by engineers to uh, cracks look for cracks in pipes. Okay, so these are some uses of the gamma rays used in the treatment of cancer, used in industries to kill harmful bacteria, to detect heart and brain abnormalities, and used by engineers to look for cracks in pipes. The next one, uses of X-rays. So X-rays are used to detect foreign bodies like coin, pen inside the human body. X-rays are used to detect, used to detect, used to detect foreign bodies, used to detect foreign bodies like pen, coin inside the human body. So, and use it to detect fracture of bones. Okay, to detect fracture, fracture of bones. To detect fracture of bones. Use it to detect foreign bodies like coin, pen inside the human body. To detect fracture of bones. To destroy malignant tumors. These are used to destroy to destroy malignant tumors, malignant tumors, and to cure skin diseases, to cure skin diseases. Okay, and in the study of crystal structure, in the study of crystal structure. Okay, so these are some very important uses of X-rays to detect foreign bodies like coin, pan inside the human body, to detect fracture of bones, to destroy the malignant tumors, and to cure skin diseases in the study of crystal structure. The next one, uses of ultraviolet rays. What are the uses of ultraviolet rays? So ultraviolet rays used in the production of vitamin D, right? Ultraviolet rays used in production, the production of vitamin D. Okay, UV lamps used to kill germs in water purifiers. Okay, UV lamps, UV lamps used to kill germs, used to kill germs in water purifiers, water purifiers. Okay, and to distinguish real germs from artificial germs. Okay, to distinguish to distinguish distinguish real germs, real germs from artificial, from artificial germs. And these are used in drying fruits, used in drying fruits, and to detect forgeries in the documents, in the treatment of skin disease, bone disease, and used in long distance photography. So these are used in long distance photography. So these are some uses of UV rays. Okay. The next one, uses of visible rays. Uses of visible rays. So we concentrate visible light to make lasers. Okay. So visible rays are used to make lasers. To laser. Laser means light amplitude stimulated emission of radiation. Light amplitude stimulated emission of radiation is laser. Okay, visible light, we concentrate visible light to make lasers to use in everything from surgery. Okay, so to use everything from surgery. Okay, and to CD players. Visible rays are used to CD players. Okay, to laser pointers, to laser pointers, laser pointers, and visible light waves also make our TV, computer, cell phone screens work. So these are some uses of visible rays. The next one, uses of infrared rays. Uses of infrared rays. So they are used in detectors and remote switches. These are used in detectors, and remote switches. Detectors and remote switches, and IR rays photographs used for weather forecasting. Okay, IR rays photographs photographs used for weather weather forecasting. And IR rays from sun keep the earth warm. IR waves from sun keep the earth warm and hence help to sustain life on the earth. So these are the uses of IR rays. The last one, that is microwave. Uses of microwaves. So microwaves are used in aircraft navigation. Okay, microwaves microwaves are used in aircraft navigation. Aircraft navigation, and microwaves are used in microwave ovens. Okay, microwaves are also used in microwave ovens. Microwave ovens. The last one, the uses of radio waves. They are used in standard broadcast radio and television, and used in short wave radio. Okay, so these are used in short wave radio and navigation. Used in navigation and used in air traffic control. Air traffic. Air traffic control and remote controlled toys. So radio waves are used in remote controlled toys. Remote controlled toys. So these are some very important uses of electromagnetic radiations. So gamma rays are used for the treatment of cancer, used in industries to kill harmful bacteria, used to detect heart and brain abnormalities, and used by engineers to look for cracks in pipes, and X-rays are used to detect foreign bodies like coin, pan inside the human body, to detect the fracture of bones, to destroy malignant tumors, to cure skin diseases, also used in the study of crystal structure. And what are the uses of UV rays? Used in The production of vitamin D UV lamps are used to kill the germs in water purifiers, and highly focused UV rays are used in the treatment of eye surgery. Highly focused UV rays are used in the treatment of eye surgery to distinguish real germs from artificial germs and to detect forgeries in the documents and in drying fruits, long distance photography. So these are the uses of UV rays. Also used in the treatment of skin disease and bone disease. Okay, so visible rays are used to make lasers to use everything from surgery. Laser means light amplitude stimulated emission of radiation and used to CD players to laser printers, laser pointers. Okay, so these are the uses of visible rays. And what are the uses of infrared rays? Used in detectors, remote switches, IRA photographs used for weather forecasting. IR waves from sun keep the earth warm and hence help to sustain life on the earth. So what are the uses of microwaves? Microwaves are used in aircraft navigation and used in microwave ovens. So radio waves are used for short-wave radio navigation, air traffic control, remote control toys. So these are the uses of electromagnetic radiation. Okay, so now let us discuss about a very simple numericals. The amplitude of magnetic field part of electromagnetic waves in vacuum, that is 510 nano Tesla. What is the amplitude of electric field part of the wave? Okay, so what is the relation connecting between amplitude of electric field and amplitude of magnetic field? That is very important. So amplitude of magnetic field is equal to amplitude of electric field divided by C, right? So here we have to find out the amplitude of the electric field, that is equal to speed of light into the amplitude of magnetic field. So the speed of light is 3 into 10 power 8 and amplitude of the magnetic field is given 510 nanotesla. So 510 nano, that is 10 power minus 9. So 510 into 3, that is 1530, 10 power minus 9 into 10 power 8, 10 power minus 1. So finally we will get so 153, right? 1530 to 10 power minus 1, that is 153. What is the unit? Newton per coulomb. What is this? Amplitude of electric field part of the wave. Okay, and next numerical. In a plane electromagnetic wave, electric field oscillates sinusoidally at a frequency of nu is equal to 2.0 into 10 to 10 hertz, amplitude of 48 volt per meter. So first we have to calculate what is the wavelength of the wave. The second one, what is the amplitude of oscillating magnetic field. And finally show that the average energy density of electric field equals to average energy density of magnetic field. Okay, so what is the expression for frequency in terms of speed of light and the wavelength? So frequency nu is equal to c by lambda. we have to find the wavelength. So lambda is equal to c divided by mu. So c is, what is the value of c? Speed of light 3 into 10 power 8, right? So the frequency that is 2 into 10 power 10, 3 by 2, that is 1.5 into 10 power 10, that is shifted to the numerator. What happens? 10 power minus 10, 10 power 8, that is 10 power minus 2. Okay, so 1.5 centimeter. So that is actually the wavelength of the wave, right? And the second part, what is the amplitude of oscillating magnetic field? So amplitude of oscillating magnetic field is amplitude of electric field divided by the speed of light. The amplitude of electric field is given, that is 48, and the speed of light, that is 3 into 10 power 8, right? So 48 divided by 3, so that is 60 into 10 power minus 8. So what is the unit of magnetic field? Tesla. Okay. And finally, we have to show that the average energy density of electric field equals to average energy density of the magnetic field. So we know that the average energy density of electric field is of epsilon naught E square. Is it not? What is this? The energy density of electric field. So what is the expression for energy density of magnetic field? So what is the relation connecting between P, E and B? So actually E is equal to B into C, right? So C is 1 divided by square root of mu naught epsilon naught. Okay, so 1 by 2 epsilon naught E square. E square is actually B square C square, right? Because E is equal to BC. So 1 by 2 epsilon naught B square. C is 1 divided by root mu naught epsilon naught square. So that is 1 divided by mu naught epsilon naught. Square root get cancels. So epsilon naught cancels. Energy density of the magnetic field is B square divided by 2 mu naught. Okay. So energy density of the magnetic field is B square divided by 2 mu naught. Energy density of electric field is of epsilon naught E square. Energy density of electric field is of epsilon naught E square. So call this as equation number 1. And energy density of the magnetic field, that is B square divided by 2 mu naught. So call this as equation number 2. Okay. So equation 1 divided by equation 2, that implies UE divided by UB. This is equal to of epsilon naught E square divided by B square divided by 2 mu naught. That is shifted to the numerator. So what happens? 2 mu naught divided by B square. So here 2 get cancels, right? So epsilon naught mu naught. Epsilon naught mu naught into E by B. E by B is actually C. Okay, so E divided by B, that is C. E divided by B square, that is C square, right? E by B is C. E divided by B whole square, that is C square. Okay, so C square, C is actually 1 divided by root mu naught epsilon naught. C square is 1 divided by mu naught epsilon naught. 1 divided by mu naught epsilon naught. So mu naught epsilon naught get cancels. So this is equal to 1. So this clearly shows that energy density of the electric field, that is exactly equal to the energy density of the magnetic field. So both are symmetrical. Energy density of electric field, that is exactly equal to the energy density of the magnetic field. Okay, so this numerical is very important. Okay, thank you.